Having just learned and summarized the basic equations of motion, let's do a couple problems. Here's a very realistic one. DHS Jr. being chased by a grizzly bear. Well, now, if you find yourself in that condition, you will run faster than you ever thought you could. I'm going to assume that you're going 11 meters per second in the first 15 meters. Well, that's really quite fast, I will admit. I'm not going to consider arguments challenging the realism of this, but I know what it's like to have the adrenaline rush and to be running pell-mell away from a bear, what I think is a bear. So I do have some personal experience with this. Anyway, what's the average acceleration? And what I want to do is graph this motion to get a conceptual understanding and then find the equation that would be most useful for solving the problem, namely the acceleration. So let's do that. So here's a velocity graph, and we have an acceleration, which is a change in velocity, where the final velocity is 11 meters per second. So there's a change in velocity that occurs given by this vertical extent here. Now, we're going to want to know the slope of the line. Well, if you remember, slope of the line is the acceleration. Okay, so we don't know what that is yet. Then if we were going to plot a position time graph, we know the final position is 15 meters, and the velocity is increasing during this time. So it's going to be a graph where the position changes more rapidly with every given additional unit of time. So that would look something like what you see. Now, what equation do we use? We must ask. And to determine what that is, you want to put down everything that the problem has. What are all the variables, the unknowns, and the knowns that are in the problem? The equation that we want to use is going to then have the acceleration that we're looking for. It's going to have the displacement because we have it, and pretty much everything we have we need to use. It's going to need the final velocity and the initial velocity. Well, also, we know what the initial position is. Actually, that is usually assumed to be 0. Sometimes it's explicitly stated as such. And if it's not listed as anything other than 0, you assume it's 0. The initial velocity needs to be understood. If it says it starts from rest, then v0 is 0, and that's the case here. Final position. Final position is given, 15 meters. Final velocity is also given, 11 meters per second. So there it is. There's all our stuff, all the information that we have at our disposal. And the equation that we would use would be one that would include that, and it's missing one very peculiar, or very obvious, I should say, piece of information, and that's time. We don't have anything about the time. So we're not going to use equation 5 because we don't have that time. So we're going to use equation 6. V squared is v0 squared plus 2ad. And we want to solve for a. So what we notice right away is we can eliminate v0 because it's 0. And then we can solve for a. A is v squared over 2d. We can just simply plug in here. So it's 11 squared over 2 times 15. And the acceleration, the average acceleration, which is a constant acceleration in this case, if not stated explicitly, at least assumed, and we get 4 meters per second squared. Now you might ask, how long does it take to get to that speed? Okay, so now we're going to actually solve for the time. Well, acceleration by definition is change in velocity over time. We know what the change in velocity is, so we can solve for the time delta v over a, which is v minus v0 over a, which is 11 minus 0 over 4, and the time is 2.7 seconds. So the problem has been solved, and the time has been derived as well. In our second example, we'll calculate the time it takes a bowler to free fall from the Sears Tower. Assuming the Sears Tower is 380 meters And that's a long way. That's like 4 football fields. Okay, so that's pretty darn high. The acceleration is assumed to be 10 meters per second 10 meters per second squared. What velocity, in this case just speed we're concerned about, as it lands. So let's make a velocity graph to begin with. So we know that the velocity increases uniformly because of the nature of the acceleration. And the slope is the acceleration, and it's given as 10 meters per second squared. Now, the area under the graph is 380. We know that because that is displacement. And the displacement is given because you start at the top and go down 380 meters. So what equation should we use? Well, let's see what we know and what we need. So we know y0. I like to assume that my initial starting point, which is the definition of y0, is just 0. So I call 0 where I start. Then the final position is 380 meters away from that. We're not going to worry about plus or minus right now. We're just going to assume positive. So as you look down 380 meters away, there's the final position. The displacement then, final minus initial, 380. Vy0, we don't throw it down, we drop it. So the initial vertical velocity is 0, and the acceleration is 10 meters per second squared. What do we need? Well, it says calculate how long. So we need time. All right. So what equation are we going to use? It has everything in here, including the time. And upon a few moments reflection, you will choose equation 5. So there it is. And now what I want to do is just go ahead and plug in. I know what many of these things are, so let's just write it down. Y, final position, is initial, 0, plus Vy0, which is 0. So we have 0 plus 0 plus 1/2 at squared. So t is just 2y over a, square root thereof. And now we can go ahead and put in y and a, which we know as well, 380 and 10. So plug that into your calculator, and out pops 8.7 seconds. So we know the time of the fall. Now, how fast is it going upon landing? Now that we know the time, we can just choose, say, equation 3 for final velocity. Final velocity is v0 plus at. v0 is 0, so it's just the acceleration times time. And that's real simple. Don't even need a calculator. 87 meters per second. And we're done with that problem.